Hi everyone, my name is Caleb Koch, and I'll be talking about the query complexity of certification. This is joint work with Guy Blanc, Jane Lange, and Liang. In this talk, we are given query access to some unknown Boolean function f and some specific input x star, and we want to generate an explanation for f's output on x star. Now there are many different ways you might formalize this notion of explanation. We'll be talking about one specific formalization. More broadly, though, this problem is motivated by explainable machine learning, where the function f is viewed as some machine learning model, and we want local as opposed to global explanations, so explanations for the model's prediction on some specific input, and we also want model agnostic explanations, so explanations which depend only on the input-output behavior of the model and not on any assumptions about the model's internal structure. Our notion of explanations will be certificates, which are well-studied objects in complexity theory. Informally, a certificate for an input is a subset of its coordinates which certify the function's output on that input. Formally, for a function f and input x star, a certificate for f's value on x star is a subset S of coordinates, such that for all strings y which match x star on the coordinates specified by S, f of y equals f of x star. As an example, suppose x star has a certificate S consisting of its first, second, and fifth coordinates. Then, whenever the first, second, and fifth coordinates are fixed to the value specified by x star, f's output stays the same, even if you perturb the coordinates outside of the certificate S. Now, notice every input has a trivial certificate consisting of all of the coordinates, because there's only one string which matches x star on all of its coordinates, which is x star itself. So we seek small certificates. For an input, the certificate complexity of that input is the size of the smallest certificate for that input. And more generally, for a Boolean function, the certificate complexity of that function is the certificate complexity of the input which is hardest to certify. And in this talk, we'll be interested in returning certificates whose size is at most the certificate complexity of f. Certificates have shown up in many different fields. Perhaps first and foremost, they've been extensively studied in complexity theory, where they are intimately tied to the notion of witnesses or proofs that are central to the study of the class NP. In learning theory, there are classic algorithms due to Valiant and Anglin for finding small certificates. And in fact, the Valiant-Anglin algorithm will show up in the design of our main algorithm. And more recently, certificates have been proposed in the machine learning literature as one way of explaining the predictions of machine learning models. We can now define the main algorithmic problem we're interested in, the certification problem. Given queries to some Boolean function f, whose certificate complexity is promised to be at the most k, and some input x star, output a certificate for f's value on x star, whose size is at most k. And we want to do this with as few queries as possible.
In general, the certification problem can be quite hard. In fact, we can show that for general functions f, there may be inputs which require exponential and k many queries to f in order to certify. For some intuition of this hardness result, notice that even if you're given a candidate certificate, you need to query f on all possible perturbations of the coordinates outside of the certificate just to verify that it's valid. On the other hand, if you restrict your attention to monotone functions, the problem becomes more tractable. In this case, if you're given a candidate certificate, you can verify that it's a valid certificate just by querying f on two inputs. The input you get by setting all of the coordinates outside of the certificate to 0, and the input you get by setting all of the coordinates outside of the certificate to 1. The Anglin-Valiant algorithm uses this observation and some other ideas to solve the certification problem for monotone functions and at most n queries. We can show that in general, monotone functions require at least k log n queries to certify. And the main result of this work is a new algorithm which solves the certification problem for monotone functions in poly k log n queries. Notice, given the information theoretic lower bound, this is optimal up to poly k factors. Before getting into our main result, let me also mention that very recently, Gupta and Manoj gave a k log n query algorithm that solves the certification problem for monotone functions. And this completely matches the information theoretic lower bound. Their algorithm is super cool, and if you're interested, you should definitely check it out. For the rest of the talk, we'll be focusing on the proof of our main theorem, which is that given a monotone function f with certificate complexity at most k and an input x star, there's an algorithm that outputs a size k certificate for f's value on x using at most poly k log n queries to f.
Suppose we are given a monotone function f, and assume for simplicity that we want to certify the all ones input. We'll illustrate how our algorithm works with respect to this specific input. Suffice it to say, all of the main ideas will generalize to any other input, modulo a few details. On the left, we have an illustration of the Boolean hypercube in 2 dimensions, which will be very useful in depicting how our algorithm works. In this diamond, the points are organized into layers, where each layer corresponds to a distinct Hamming weight, and higher layers correspond to higher Hamming weights. So at the topmost layer, you have all strings of Hamming weight in, of which there is 1, the all ones input. On the bottom layer, you have all strings of Hamming weight 0, of which there is 1, the all zeros input. And the middle layer, the widest layer, which contains the most points, is the layer consisting of all points of Hamming weight n over 2. With this picture, we can nicely illustrate the function f by shading in all of the points on which f evaluates to 1. This forms the 1 region, and notice because f is monotone, this region is necessarily connected, and it forms this distinct zigzag-like border with the 0 region. Now, with this picture of f, we can make 2 useful observations. First, notice that every 1 input corresponds to a certificate for x star, the all ones input. In particular, if we have some 1 input y, if we take the certificate consisting of all of its 1 coordinates, this must be a certificate of x star, because regardless of how we perturb the 0 coordinates, the function must still output 1 by monotonicity. Second, we notice that all of the min terms of f must have weight at most the certificate complexity of f. A min term here is just a 1 input, all of whose lower Hamming weight neighbors lie in the 0 region. So for this function that we've illustrated on the left, there are exactly 4 min terms. The weight of each min term is at most the certificate complexity of f, because if you look at any one particular min term, the certificate complexity of that min term is at least the Hamming weight, because you have to fix all of the 1 coordinates in order to ensure that the function evaluates to 1. And this necessarily lower bounds the certificate complexity of the function overall. This is useful to us because it shows in particular that if we want to certify the all ones input, it is sufficient to just return any min term, because any such min term will correspond to a small certificate. We've now reduced the certification problem to the problem of finding a min term. And to find a min term, our algorithm starts at the all zeros input and then performs an upwards walk of length at most poly k that hits the 1 region. Then, once we've hit the 1 region, we can simply apply the Anglin-Valiant algorithm for certification to walk down to the midterm within this one region.
Let's look at an example to see what the steps in our upwards walk might look like. Each step corresponds to fixing some coordinate to 1. When we fix that coordinate to 1, we add it to a candidate certificate, which we maintain as we perform our walk. On the left here, you see an example of what might be the first 3 steps in our upwards walk. Starting at the all zeros input, in the first step, we set x3 to 1, and we add 3 to our candidate certificate. Then we zoom in on the Boolean subcube, which corresponds to strings with x3 set to 1. Equivalently, we zoom in on the subfunction of f obtained by restricting x3 to the value 1. In the next step, we set x9 to 1, and we add 9 to our certificate, and then zoom in on the subfunction obtained by setting x9 to 1. We repeat this process until eventually we've hit the 1 region. Equivalently, we've zoomed in on the subfunction obtained by restricting f according to the steps in our walk, which is the constant 1 function. How do we know which step to make in our upwards walk? Equivalently, how do we choose which coordinate to add to our candidate certificate? Remember, we want a short upwards walk that hits a 1 region. Equivalently, we want to find a coordinate xi such that the restriction of f by setting xi to 1 is close to the constant 1 function. But differently, we want the distance between the restricted function and the constant 0 function to be large. This distance is just the proportion of inputs on which the function evaluates to 1, and since the function is Boolean valued, this is just the expectation of the function. This suggests a very natural first attempt, which is to just take the coordinate xi that maximizes the difference between the expectation of the restricted function and the expectation of the original function, where both of these expectations are with respect to a uniform random input. There's a problem here, though, which is that these expectations can be exponentially small in k. And so to estimate them accurately enough, we may need exponentially many random samples, which corresponds to exponentially many queries to f. To overcome this difficulty, we'll look at a slightly different distribution over inputs, for which we can tolerate weaker expectation estimates. Specifically, we'll look at the p-biased product distribution for a carefully chosen value of p. Recall, this distribution is a distribution over strings such that each coordinate is sampled independently as a p-biased coin toss. We can look at the p-biased expectation of f as we vary p from 0 to 1. If f is non-constant, then the p-biased expectation will be 0 when p is 0, and the p-biased expectation will be 1 when p is 1. And if f is monotone, the function in between will be a monotone increasing function in p. In particular, there will be some value p star for which the p star biased expectation of f is exactly 1/2. This value p star is known as the critical probability of f. For some intuition, suppose f is biased towards 1. So in the vast majority of inputs, f evaluates to 1. Since f is monotone, intuitively, the more 1s there are in the input, the more likely the function is to evaluate to 1. So, if f is balanced over some distribution, that distribution needs to place large weight on strings which have a lot of zeros in them, and little weight on strings which have a lot of 1s in them. So in this case, the critical probability will be some value of p which is very close to 0. So now going back to our upwards walk, instead of looking at expectations over a uniform random x, we'll look at expectations over the p star biased product distribution, where p star is the critical probability of f. This way, both expectations will be larger, and we'll be able to tolerate much weaker expectation estimates. We can now write down the algorithm for our upwards walk. In each step, we start by estimating the critical probability p star of f. Then, For each coordinate I, we estimate the difference between the p star biased expectation of f with xi restricted to 1 and the p star biased expectation of f. We then take the coordinate I star, which maximizes this difference, and we add I star to our candidate certificate. We then recurse on f with xi star restricted to 1. We can then show that if f is a monotone function with certificate complexity at most k, then this upwards walk will hit a 1 region within at most poly k steps. Moreover, we can also show that each quantity in this algorithm can be estimated to high enough accuracy with at most poly k log n random samples to f, and hence at most poly k log n queries to f. In order to show that each step in our walk brings us closer to the 1 region, we need to show that each step brings us closer to the constant 1 function. And to do this, we show that the critical probability drops significantly after each step. In particular, we can show that the difference between the critical probability of f and the critical probability of the function obtained by restricting according to the step that we make is at least 1 over poly k. And so in each step, we make additive 1 over poly k progress towards 0. Notice this makes sense since it shows that f is becoming more and more biased towards 1, and hence our upwards walk is getting closer and closer to the 1 region. If f is non-constant, then necessarily the critical probability is strictly greater than 0. And so we know f must be constant when the critical probability hits 0, which occurs after at most poly k steps. Zooming back out, we've just described the first stage of our algorithm, which is an upwards walk of length poly k that hits the 1 region. Once we hit the 1 region, we apply the Anglin-Valiant algorithm to walk down to a midterm. The Anglin-Valiant algorithm works by greedily removing coordinates from the candidate certificate which are unnecessary. Since our upwards walk has length poly k, when we hit the 1 region, we have a candidate certificate of size at most poly k. Thus, the Anglin-Valiant algorithm requires at most poly k steps before it hits a midterm. As we discussed before, every midterm corresponds to a size k certificate for our input. So, once we find a midterm, we're done. With our algorithm in hand, we can prove that given queries to a monotone function f, whose certificate complexity is at most k, and an input x star, we can output a size k certificate for f's value on x using at most poly k log n queries to f. In the regime where k is small, let's say poly log n, this yields an exponential improvement over the previous best known certification algorithms, which used a linear number of queries to f. In conclusion, let me just highlight one interesting aspect of our algorithm and some future directions. A key part of our analysis was the use of the critical probability as a progress measure. We know that our algorithm is efficient because in each step, the critical probability of the underlying function shifts by a large amount. As the critical probability changes, our algorithm adapts to the new critical probability. Previously, critical probabilities came up in the study of Boolean functions and random graphs, but to our knowledge, it hasn't been used much in the design of algorithms. It's natural and interesting to ask whether there are other learning algorithms that could benefit from the use of the critical probability as a progress measure. There are also a lot of interesting and natural questions related to local explanations and learning. For us, we use the Anglin-Valiant algorithm from learning theory in the design of our own algorithm. What other connections are there to learning theory? And also, what other tools from learning theory can be used to design algorithms for local explanations? Relatedly, what other notions of local explanations are there? In particular, what other notions of local explanations admit query-efficient algorithms? For us, we only studied one notion of explanations, certificates, but there are many others that one could consider.